Thanks very much for the invitation. This is joint work with Florian, who's here. I guess we've been working on this for something like 8 years now. It's been a long time, and hopefully this process is now coming to an end. You've probably seen various versions of this paper presented here and there. So it's called Differential Games of Public Investment. I have a pet title. It's very nice to present 1 week after Pierre, because at least one of the issues that Pierre raised in his recent critique of differential games as they've been applied in economics is actually exactly the issue that we sort of started trying to fix 8 years ago. And it's taken a while because it gets very technical, but we hope that you sort of we hope that you read it, and hopefully that you appreciate it as well. So my pet title for this paper is How I Learned to Stop Worrying and Love the Differential Game, because we have two main results here in the paper. And the first one is the How I Learned to Stop Worrying bit, in which we sort of argue that we fix some of the foundations of differential games. That might be quite a sort of a strong way of putting it, but let me put it out there. And if you want to disabuse me of hubristic notions, then please go ahead. And the second part is the Love the Differential Game bit, where we give very convenient conditions that you can use in practice to analyze these types of games. And it turns out that continuous time is very powerful in terms of tractability. And you can do many things which I think you couldn't, I'm pretty sure you couldn't do in discrete time games, which are obviously used a lot in economics. So we hope that more people might sort of explore continuous time games. So I know that this is probably the sort of most expert audience that I've presented this paper in front of in this particular topic. But I hope you will excuse me if I first just spend a few minutes on a slightly infantilizing example, perhaps. I hope you don't think it's too infantilizing. I found it to be useful, at least for some audiences. So it's an analogy, which I call the children's game. So this is a very standard, undergraduate environmental econ 101 public goods game, where you have two players. Everything is symmetric. The players are row and column. They have two choices that they can make. They can either emit a pollutant, which gives them a private benefit of 4. You get a high benefit for not abating your emissions and using fossil fuels, but then you cause an externality of -2 to yourself and also to the other player. And the second thing you can choose is you can choose to not emit, when you get a private benefit of just 1, less than if you use fossil fuels, but there's no externality. So, you can add up all this sort of payoffs, and it turns out it's a standard prisoner's dilemma that we've all, taught to our undergrads if we've taught undergrad environmental economics. And the only Nash equilibrium is both emit, and that's inefficient, because the efficient outcome is both not emitting. That's the outcome that maximizes joint welfare. Now, so this is an analogy to what happens in differential games. Suppose that we are mathematically not sufficiently sophisticated. Suppose that we are 5 years old and we don't understand negative numbers. So, you try and compute some of these payoffs. You think one player emits, the other one doesn't. Then the payoffs involve taking 2 away from 1. If you're 5 years old, you don't understand what that means. So we're confused about these two cells in the payoff matrix, because we don't understand negative numbers. What do we do? So the one option that what we could do is we could just conclude that, well, the problem is with this action that gives us -2. It's the subtraction that leads us to the problem. So you could rule out any actions that involve subtraction. And you do that, then the only remaining outcome is neither player emitting, and then trivially that's also a Nash equilibrium. And that might be your conclusion from this game. But of course, we are analysts, we understand negative numbers, we have PhDs, so we know that the true equilibrium of this game should be emit, and that's the only Nash equilibrium. So that's one thing that you could do. The second strategy that you could take to tackle this problem is to rule out strategy profiles, which involve negative payoffs. So you might rule out these corner payoffs here. But this would be a restriction on strategy profiles. And it would mean that if I'm a row player, and if I believe column will play not emit, then the only thing I'm allowed to choose is also not emit. Because this cell here isn't, this strategy profile here isn't admissible, so to say, or playable. And neither is this one. And then we might conclude that there are two Nash equilibria to this game. But of course, that's the incorrect conclusion as well, because we know that the only real Nash equilibrium here, if you understand the maths, is that everybody emits. So you know, this kind of a thing has been, this kind of a problem has bothered differential games as well. Of course, the sort of the sort of problematic mathematics are a bit more difficult in the case of differential games, but these two strategies have been taken by researchers looking at these problems. Now let me outline a little bit more what I mean. So here's a differential game now, and this is what we're all familiar with. We have n players indexed by I, and they all maximize the sum of the, or the integral of the discounted flow utility from here to infinity. They all have some discount rate. They have a flow utility which depends of a player I on their own action Qi and on the state variable X. And you, of course, choose the trajectory of your action variable, and that gives you your value function given any initial state x0. Now, importantly, I'm going to emphasize a few things here. One of the things is that we rule out any payoff, any interdependence of the actions in terms of the payoff. So some other players' carbon emissions, for example, don't directly affect my welfare, except via the effect that they have on the stock. So here's the state evolution. This would be, in the example that we're using, this would be the atmospheric carbon stock. The time derivative of the state variable is some function of the current state, and then the vector of all the actions. And the initial state is given, it belongs to some compact set on the real line. So that's an important assumption that we make. We're going to be entirely here in the space of, in the sort of realm of one-dimensional differential games, so just one state variable, okay? So what are we looking for? We're looking for Markov-perfect Nash equilibria, which we're considering Markovian strategies phi I, one for each player, which condition that player's action Qi at time t on the state at time t only. So this would be the rule how the players were using Markovian strategies would set their actions at each point in time. They observe the carbon stock in the atmosphere, they consult their strategy book, and they pick their emission rate. And that's it. And then, of course, a Markov-perfect Nash equilibrium is a collection of these policy rules, one for each player, such that for each player, the rule that they've chosen is a best response to the rules chosen by the other players for any initial state. So this is very standard and familiar to all of you. Now, where is the mathematical issue? This is one of the things that Pierre emphasized last week. It lies in the fact that once we take this Markovian policy rule, these Qi's, and substitute those into the vector Q here, then the right-hand side of this differential equation is a function of just the current state X. And then the question is, well, can we compute the solution to this differential equation for any initial state? And when can we do that? Well, we know from the theory of differential equations that we can certainly do that if the right-hand side is Lipschitz continuous then in the state. But that requires that not only does f have to be Lipschitz continuous in X and Q, but also this strategy function phi I for each player has to be Lipschitz continuous. And that's a bit of a problem, because we know that we can come up with we can take the other player's strategies phi not I, have them be perfectly smooth and nice, differentiable, everything, and yet come to a situation where player I's best response to that is not even continuous. In a situation where we have schema points, for example. So the other players might play something that mimics, that has non-convex dynamics, mimics a shallow lake, for example. And then the best response by player I would be not Lipschitz continuous. So it's a bit awkward to a priori try and restrict the space of functions that we can choose to be, for example, Lipschitz continuous. So what if we allow discontinuities in these policy rules phi I? Well, then we are no longer guaranteed a unique or a unique solution to this equation, or even the existence of a solution to this equation. And so what's been done in the literature is often many papers a priori say that they are only interested in equilibria in continuous strategies. So that would be in my previous analogy, that would be the equivalent of ruling out strategies which involve subtraction. Or they say that they are going to only look at admissible strategy profiles, that is, strategy profiles where you don't run into any problems. But then that implies that what I'm allowed to choose as player I depends on what the other players are choosing at the same time. So the main question here is that we're trying to tackle is, are differential games actually games in the sense in which John Nash defined non-cooperative games in 1951, in particular so that all the players can have a strategy set that they can choose from independently of what the others are choosing at the same time. So if we restrict strategies to be Lipschitz continuous, then yes, we can always compute the trajectory, we can always compute the payoffs, and we are dealing with a game in the sense of Nash, loosely in the sense of Nash. But the problem is that then to many strategy profiles of the other players, player I doesn't have a best response in the same strategy space of Lipschitz continuous functions. And another problem is that, in fact, making this restriction, you may miss out perfectly well-defined equilibria, in which the dynamic equation does have a classical solution, even with discontinuous strategies. So you may sort of fail to see many equilibria, which we will show is actually can very well happen because of this restriction to Lipschitz continuity only. So the second option has been to impose this admissibility restriction on strategy profiles. But because that's a restriction on profiles rather than strategy sets, then you're no longer dealing with a game as John Nash sort of specified a game to be. So let me give you, I hope everything is clear. So please chip in at any point if you have any questions of clarification.
Niko, I have a very basic question. I saw
Yes.
that for a game to qualify as a game, you have to be able to write down the normal form. So if you take a differential game and you can write it in normal form game, I think you can claim that it is a non-cooperative game in the usual sense. Now you are going one step further by discussing the strategies and the solution themselves. So I'm a little bit here confused somehow.
Okay. Yes. So if you think of this as a normal form, if you think of a differential game, the way we think about it is we think of them as normal form games where the sort of actions that you choose are these policy rules phi. And then in the normal form analogy, the payoff matrix doesn't have scalar payoffs, but it has value functions, because you have to think about best response from any initial state. So you're comparing value functions. And the problem is that with discontinuous strategies, there's many situations where you don't even have a classically defined solution to the dynamic equation. So you don't know the trajectory of the state and thus of the actions, and thus you can't compute the payoffs. So you leave many cells in the payoff matrix, empty, so to say. And that's what we are trying to solve here. Does that answer your question?
In fact, it's a matter of terminology, not as deep as you are answering here. But anyway, please go ahead.
Okay. Well, we can see. Let's see how this goes, and feel free to ask more questions later. So let me give you a summary of our main assumptions here, and then the two results. So first of all, we define a strategy space S which is the space of real analytic functions that have a finite number of discontinuities. And you know, there's little details over and above that, but let me skip those. So we take, and what is real analytic? I mean, you know, don't ask me to give you the precise definition, but it's basically stuff that's infinitely differentiable, and where no derivative goes to vertical. And if you want more precise than that, Florian will answer. But let me say that, you know, real analytic basically covers almost all the stuff that we are dealing with, at least as long as you sort of sometimes have to rule out, you know, particular bits where things like marginal utilities go to infinity or something. And we're looking at piecewise functions formed from these kinds of pieces, and that's the sort of strategy space S. We say that the primitives, the flow utility and the dynamic equation, that those are also real analytic. We are here imposing that the flow utility is increasing and strictly concave in my own action, because our main example, as I said, was non-cooperative mitigation of climate change. So we can think of the own action as carbon emissions, and then my flow utility is increasing and strictly concave in that. And then it would be decreasing in the state variable x, because x is the carbon stock, which gives you damages. But you can always reverse some signs to turn this into, you know, a joint investment in a public sort of stock good problem, or you can look at renewable resources, controlling a shallow lake. I think you could probably use these results for particular types of learning problems, like strategic experimentation problems, where the state variable would be something like a shared belief over whether a particular choice is good or bad, which you don't know ex ante. But we haven't thought about that very carefully, so let me just emphasize that that's a conjecture. So the dynamic equation here is going to be such that the carbon stock here grows with the sum of all emissions, and then there might be some sort of natural dynamics based only on the current stock. And finally, because we say that the state space is a compact set on the real line, we also specify exit payoffs beta at both ends of the line, in case you might want to exit the state space. So this is dealing with one of Pierre's criticisms from last week, and I'll say a little bit more about that in a second. Okay, so the main results, which are what we see the paper is as, you know, the paper's main contributions. Theorem 1 is the how I learned to stop worrying theorem. It's saying that basically, perhaps I've written this a bit too technically, but if you fix a bunch of discontinuities where you are connecting these pieces together, and you say that the other players are playing a strategy coming from the space that we defined of piecewise real analytic functions with these particular discontinuities, we're going to ignore this here, then basically player I has a unique best response, which is in the same function space. So this is saying that the best response correspondence is well defined in that if you feed a bunch of a strategy profile to the best response correspondence, then it spits out something that's also in the same function space that we started off from. So the differential game is basically well defined, and yeah. But there's this exceptional set EJ, which is a set of strategies such that player I, in fact, doesn't have a best response in the same space. I can say more about that in a bit, but let me start by saying that it's a Shy set, which is an infinite dimensional analog of measure zero. So that's to say that in terms of what George was saying, almost all the cells of the payoff matrix here would be filled in. So we can always compute the payoffs, and almost always we can find a best response to any collection of strategies by the other players, except for this funny exceptional set. And this is the result which basically makes differential games well specified as games. anything can be played, all the payoffs can always be computed, and it's a nice feature that you also almost always have a best response. Second main result, why you should love the differential game. It's basically we give a necessary and sufficient condition that helps you construct the best response for player I. Of course, you can then sort of say, let's take a fixed point of this, and that would be a Markov-perfect Nash equilibrium. And it's very, it looks a bit horrible once you look at it. At least that's what some of the feedback from readers has suggested, but it's actually very easy to use. It's a kind of a cookbook style thing. The way I like to think about it is it's a little bit like the Pontryagin maximum principle necessary conditions, except that this is for Markov-perfect equilibria and it's necessary and sufficient. So, if you have a graduate student who has an application in mind which fits our assumptions, then you can give our theorem 2 to the graduate student and tell them to apply it mechanically. Not quite mechanically, but in a straightforward manner. Assuming that you trust our maths, and there's a lot of maths in the appendix. But if you think that, if you trust that we've done it properly and we've tried to do our best, then you can just apply it. Okay. Just a quick aside.
May I interrupt, or
yes.
is it the right time? If
yes,
I may interrupt,
go on.
I object to referring to a Pontryagin maximum principle, because very deeply in the statement of a Pontryagin maximum principle, there is the fact that the adjoint vector is continuous, while in this situation, the adjoint vector may not be continuous. So you cannot compute it just by integrating one trajectory, assuming that the adjoint is continuous. It might not be.
I agree. I fully agree. So I meant, with my reference to the maximum principle, when I was in graduate school first year, I learned optimal control, and there was a sort of and sometimes when I teach optimal control these days, I give students a bunch of necessary conditions and then I show them how to use it. That's the only sense in which I sort of wanted to relate to the maximum principle, in that it's a sort of a, we give a bunch of fairly easy to use conditions to construct these equilibria, but of course they look very different, and the way you use the conditions is very different compared to Pontryagin. So it was only meant as a very loose analogy to the ease of use of what we think of as the ease of use of our theorem 2. Okay, so I don't want to sort of, I didn't mean that in any deeper sense. So let me address Pierre's 2 main criticisms from last week and from his note in JET. The first one was the time horizon in Tutsu and Mino, a classic paper, where they start off with an infinite horizon problem, and then it sort of changed, a little bit sort of unexpectedly into actually a free end time problem, because the state space turns out to be endogenously actually constrained or bounded. So we make here the free end time explicit. So we have these exit payoffs and we have the compact state space, and in principle you might be able to exit the state space. So in that sense, we're in line with that particular criticism. But I would argue still, though, that for many problems at least, you can effectively set up problems which are basically infinite horizon by choosing the boundaries of your state space well enough. So in the example that I'm going to show, we're going to have boundaries of the state space such that if you start from the interior of the state space, then you will never be able to reach the boundary so that you could exit. So in that situation, effectively you're dealing with an infinite horizon problem.
Yes, but this was not the situation in the Tutsu in Mino paper.
Yeah, sure. I agree with that. The second criticism that Pierre made was this fact that you have this admissibility or feasibility or playability restriction on strategy profiles. And that's exactly actually the point of our paper. We want to eliminate such restrictions so that the resulting model is basically analogous to a standard non-cooperative game. as defined by Nash. So that's the relation to Peirce pieces. And it's very nice, actually, you know, given that we've been working on this for a long time, it's very nice that you've pointed this out, because we thought that this is an important problem. So that we're solving. So well, okay. So given that we are with you know, that this is a bunch of experts on this particular topic, I thought that I would say just a little bit more of how we deal with discontinuous strategy profiles. So I think I've said most of this. Our strategy space S is the space of piecewise functions with finite number of discontinuities or pieces. The pieces have to be real analytic on the interior of each piece. And then if you take the sort of, if you take the closure of those interiors, then basically the function has to be at the points, it has to be continuously differentiable at the cutoff points. And what we then do is we use Filipov's theory of the, I guess it's non-smooth control or differential equations with a discontinuous right-hand side to think about how we define trajectories in classically problematic cases. And then we also have to adapt the payoffs in these problematic cases so that they make economic sense, so to say. So let me just quickly go here to explain Filipov and how we define the payoffs. So fix strategies by the other players. Just think about player I's problem. Then we define for any x in the state space, we define the set of dynamics that are achievable by player I, given what the other players are doing. So it's the set of all the actions in the control space. Well, it's rather the set of all the dynamics which are achievable by some action by player I in the control space. And then we think about, at a point x, we think about the left-hand limit of this set of feasible dynamics and the right-hand limit of this set of feasible dynamics. And a Filipov solution is then basically an absolutely continuous trajectory, x, time trajectory, and a measurable control trajectory, such that for almost all t, it satisfies this differential equation, where we basically take the convex hull of the left and right-hand side limits of these feasible dynamics. So that if you have situations where, I mean, the main situation, there's two funny situations. One is something that's in principle, you know, doesn't sound so problematic, where you are at a point where you are being pulled to the left and to the right. So usually we might think of that as a schema point situation. In principle, given our specification, you might even stabilize there with some sort of a convexified control. The other situation, which is perhaps a bit more problematic, is a situation where you are being pushed from two directions towards the same point at a strictly positive speed. So you might get a chattering outcome where you don't have a classical trajectory, but it's obvious that this point should be a steady state. So the key question is then, so you don't have a classical situation where this point would be a steady state, but you would have a Filipov solution. And then the question is, how do we compute the payoffs? So at this kind of a situation where you have a discontinuity in the state space at x bar in the other player strategies, and then you have a situation where the state is stabilized at this x bar for some interval of time. Then in that situation, a player I is going to choose three things. So in a way, we expand the control set. You choose a sort of a left control and a right control, and then a weight. And the player has to choose them so that, given the left and the right control and the weight that they put on the left control here, the weighted average of the dynamics is equal to 0. And then using the same weight, we take your flow payoff is then the weighted average of your left and right hand flow payoff. So you know, in principle, this would allow situations where you sort of play a weighted average of two different actions, which are sort of flickering back and forth infinitely often. And what this specification implies that, if you are being pushed away from the right-hand side much more strongly than from the left-hand side, then in a way you spend more time on the left-hand side, and your flow payoff then puts more weight on the left-hand side flow payoff. That's the sort of intuitive interpretation of this kind of a push-push, where you be in situation where you are being pushed towards a point and you're chattering there. Now I'm going to say at this point that perhaps this notion of chattering makes you a bit uneasy from an economic perspective. So I'm going to tell you that our results, even though we have to allow for this possibility, our results imply that it's actually never going to happen in equilibrium. And in fact, it turns out that all the equilibria that we derive, in fact, have the dynamic equation has a fully classical solution. So we allow non-classical solutions, but in the end, once we get our necessary and sufficient condition, those actually never arise. Okay, I hope that's somewhat clear. It's perhaps a bit much. Okay, so let me say a little bit. We also have an application in the paper. It's mainly meant as an example of how you use our results. So we take the very classic Van der Ploeg, de Zeehof, Dockner and Long model of non-cooperative climate change mitigation. The intention is just to demonstrate how you use our methods in any particular application. I mean, we chose this one because everybody knows it. But you could choose other functional forms. You could choose, many other things, and look at other applications basically. What do? We get the entire set of symmetric Markov-perfect Nash equilibria. This is something that I think in an analogous discrete time model you couldn't do, and that's that's basically because continuous time, as I said, is very powerful, and in particular this kind of a context. In discrete time, you would have to pull out of the hat an entire value function, sort of fully formed, and then show that that's consistent with an equilibrium. Here we can construct the value function bit by bit from the Hamilton-Jacobi-Bellman equation and some other conditions. So we get to this well-understood model, we get a bunch of novel results, which we think are sort of independently of interest. So first of all, it's a linear quadratic setup. So there's a piecewise linear strategy equilibrium, as you often get in these kinds of models. And because we look at the set of symmetric equilibria, they can be Pareto ranked. And it turns out that in the space of equilibria with a continuous value function, the linear equilibrium is Pareto dominated, at least weakly, by any other equilibrium. So in a sense, it's the worst thing you could look at least as long as the value function is continuous. And this is interesting, and I'll try and say a little bit about that, why I think that is the case. We show that you can sustain the first best steady state as a Markov-perfect equilibrium, so which is then a self-enforcing outcome, even when you have a strictly positive rate of pure time preference. I'll say a little bit, we sort of try and answer the question, well, does this matter? Is it important? From, for example, a welfare perspective. And we show that, at least in our calibrated example, it's a simple example, but still, it actually is quite important. And then we show the existence of these funny equilibria which actually have a discontinuous value function, where there are these strategic traps where you can get stuck at very high levels of carbon concentrations that you really would want to sort of escape this trap, but you are unable to individually do it. And everybody would want to do the same thing, but nobody can do it by themselves. And then they end up playing, something very bad, which pushes the carbon concentrations even higher. I might not have the time to get into that, but I'm happy to answer any questions about that, of course. So, but here's the sort of big potatoes, small potatoes. Does this matter question? So what we have here on the horizontal axis is the state. And on the vertical axis, we have welfare relative to two benchmarks. The 100% is, of course, the first best, the socially optimal outcome. The 0% here is a non-equilibrium outcome in which there is no climate policy at all. So all countries are polluting at their bliss point level. That's not even an equilibrium, okay? But it's just something that we chose in order to calibrate the other end of the scale. And now the linear equilibrium gets you here, gets you something like about 55% of the surplus between this non-equilibrium sort of business as usual outcome and the first best. And then if you take the best symmetric Markov equilibrium that you could for any initial state, then you get this envelope of welfare, which shows that, you know, the sort of, if you play the right equilibrium, you can actually close more than half and even 100% of this welfare gap that remains between the socially optimal and the linear equilibrium. So it seems that this is an important, in terms of welfare, result. And we were asked a little bit about policy implications of this. I'm hesitant to make strong policy claims because it's such a simple model. But one thing that I've sort of concluded is that perhaps a policy implication is that we might want to think of climate negotiations more as a cooperative effort to make sure that we don't play a bad equilibrium. And perhaps that we might even play a particularly good equilibrium, rather than viewing them as a as this non-cooperative exercise in playing a dynamic prisoner's dilemma and trying to squeeze as much welfare as we can out of our sort of partners in the negotiation. You know, these infinite horizon strategic situations, they often have multiple equilibria, and we might want to try and think about, well, how do we choose the best equilibrium? Okay. In terms of the literature, I mean, Pierre had a lot of references to this playability or admissibility issue. I've only included 3 classic textbooks which discuss a little bit this issue. So it's been an open question for a long time. These admissibility conditions also come up in a lot of the learning literature with strategic experimentation, like with Keller, Ruddy and Cripps, Klein and Ruddy, and other papers. And of course, Pierre discussed the admissibility issue as well. Technically, we use a lot of viscosity solutions. So of course, Yuli Sannikov has done a lot of work with those in economics. We use, we extend and apply methods by Barles and co-authors looking at control problems with discontinuities, basically. So we sort of took a lot of inspiration from them, but we also had to push these methods a bit further because we need to work in situations that they can sort of abstract away from, because we are interested in equilibria. We can't rule out anything. The other players' dynamics are going to be endogenous, ultimately in equilibrium. And then, of course, there's a long literature, and this is missing so many papers. You know, there could be a page full of papers here about non-cooperative dynamic public goods games, particularly with an application to environmental questions. So I've mentioned a few here. I could have mentioned many, many more. Okay, so I have about 12 minutes maybe. So let me get a little bit more concrete, and let's explain how we use our methods in the application. So the Van der Ploeg, de Zeeuw, Dockner Long model is linear quadratic. There's a flow utility, which is a function of the state variable carbon stock in the atmosphere and my own emissions. Emissions are increasing and strictly concave. And there's a bliss point, of course, in my own emissions, and then there's some convex damages. And the carbon dynamics are such that everybody's emissions add to the carbon stock. There is some geometric decay from the carbon stock with carbon going to the deep ocean or something. So this is now a symmetric game. It's now a linear quadratic game, so it's a particular functional specification. What our results hold for many others. Each player has a bliss point for emissions. So we then naturally set the control set to be between 0 emissions and this bliss point emissions. No player would ever want to pollute more than that. And then we set the state space to be basically the space of all the carbon stocks that you could potentially sustain, given that you never can emit more than the bliss point and given the carbon dynamics. So if you start in the interior of this interval, you can never reach the point 0. You can never reach this upper bound either, and thus, we need to specify the exit payoffs, but they don't really play any role in the solution to the game. So it's well known that there's a unique piecewise linear Markov-perfect equilibrium, although, okay, so it depends on the parameters. There can be another, so it might not be unique, as Colin Rao showed. You can solve this basically by guess and verify. There's many nonlinear equilibria, like Dockner and Long showed, but the problem is that they are not, in the analysis for Dockner and Long, they are not globally defined. So the strategies are not defined on the entire state space, and that's, of course, problematic. So Colin Rao had classified continuous strategy equilibria, and then Pierre, of course, discussed Colin's contribution as well last week. So this is now the space of a plot where we draw strategies. So we have the pollution stock here, we have symmetric emissions here, individual players' emissions, and we're only looking at symmetric equilibria. And these curves that I've plotted are basically they're curves which solve the Hamilton-Jacobi-Bellman equation. And of course, we're looking for a function here, so we can't, basically all the strategies have to follow bits of these curves, and then we can stitch them together in particular ways that we show. You can never, because we're looking for a function, you can never have a strategy which would bend back on itself. It would no longer be a function. So you would have to discontinuously connect it in some way. And we show you how to do it. So the linear strategy would be this one here. Low carbon stocks, high emissions. So the state grows, you're moving to the right. If you have very high carbon stocks, then you have low emissions and you're moving to the left as the natural decay overpowers the player's emissions. And there's a steady state at this point. And of course, there's a whole line of potential steady states given by the dynamics. Dockner and Long drew attention to this green bit here and the steady state at the end of it, saying that this is a particularly nice equilibrium because you can sustain it as an equilibrium, and there's and the steady state has lower carbon stocks in the long run than the linear strategy does. But the problem with this curve here is that if you extend it using the Hamilton-Jacobi-Bellman equation, then this red bit here to the left of the steady state is no longer part of an equilibrium strategy because it involves very low emissions going to zero carbon stocks, zero emissions. That basically breaks a transversality condition. So there was a question, well, what do you do with a strategy that's defined only in part of the state space? We show how you can connect these kinds of strategies so that they cover, you join them discontinuously with other patches or other strategies so that in the end they cover the entire state space. How do we do this? So I'm going to return to this graph in a second, but let me summarize and perhaps paraphrase our necessary conditions now adapted to a symmetric Markov-perfect equilibrium. So a strategy phi and the associated value function are a symmetric Markov-perfect equilibrium of this game if and only if, basically where you have a continuous strategy, you satisfy the Hamilton-Jacobi-Bellman equation. The value function cannot be increasing. If you play a strategy which involves stabilization at a point of discontinuity, then it has to be that one of the arms of the strategy has to lie exactly on the steady state locus. So you cannot stabilize in a way that chatters, for example. But one of the arms has to lay exactly on that locus. And finally, if you have discontinuous value, that can only happen if none of the players can single-handedly. So it's going to be a discontinuity where the value falls as you move to higher carbon stocks. And if you're just on the bad side of that discontinuity, then it has to be that none of the players can single-handedly drive the system back to the good side. Because if they could, of course, then they would get the value on the good side. And if they're very close, the value function wouldn't be discontinuous to begin with. So you can only have a discontinuous value outcome if there's a lack of controllability on the bad side.
If I may
Yes.
say one word, this is exactly what Isaacs calls semi-permeable surfaces.
Okay, that's very good.
That's Isaacs' condition of semi-permeability.
Great, thank you. That's good.
But you find it also in optimal control in the book by Kara Theodory, between in the 1920s, where he has this problem called the Zermelo problem, he calls it. And he has a discontinuous value function, and with this condition also. This is 1924, something like that.
Perfect. I see Florian is writing things down. That's
1935 is the...
Yeah, good. So let me now quickly show how so these are a bunch of local conditions, and we can then use these jointly with the solutions to the Hamilton-Jacobi-Bellman equation to infer some global conditions restricting the set of possible equilibria. So, for example, we can say that these gray areas here, no equilibrium strategy can pass through this gray area, basically because if you pass here, you cannot discontinuously connect this with another arm, because here below the steady state locus, you're of course moving to the left. And if you were to try and connect this with something, continuity of the value function would imply that you can only connect it with something over here, but then that would give you a chattering outcome, which one of our necessary conditions rules out. So we can rule out a bunch of, these two regions here. We can also rule out in the continuous value case, these two regions, because we show that the necessary conditions imply that you cannot continuously, with a continuous value, you cannot extend an equilibrium across the entire state space. And then we put the two sort of forbidden regions together, and what's left here in white is where possible equilibria can pass. And in fact, you can take any point here in this white region and start extending from that point to left and to the right and construct an equilibrium strategy with an arbitrary number of discontinuities as you please. It's very easy to do. So computation of these things is actually, it's not quite trivial, but it's not very difficult. And I say this as someone who's spent hours sometimes watching MATLAB converge on a policy function iteration problem like this. So computation becomes very easy. Okay, so in the example, I don't want to put too much weight on this, but in the example, we sort of say, well, what would be the Pareto optimal strategy from today's state? Today's state would be something like 0.5 gigaton of carbon, so we'd be somewhere here to the left of this, and the Pareto dominant strategy equilibrium would be such that we set very high emissions for, I think, about 10 years, a little bit more or less, and then we discontinuously stabilize, decarbonize into a steady state, and this nice steady state is sustained by the fact that if for some reason we were to ever drift a little bit higher, then all the players would start increasing their emissions, then they would increase their emissions a lot, and ultimately you would end up in this steady state with much, much higher carbon stocks. So it's the threat of ending up in a very bad steady state that sustains this good steady state here. And this would be potentially, but again, take this with a grain of salt, policy implication, which would be that perhaps we should structure our climate agreements so that, we say that we're going to aim for stabilizing atmospheric carbon at 470 parts per million. But if we miss that, then the next stop is going to be 540. And it would be this threat of ending up much higher, which could actually sustain efforts to stick to the more ambitious target. Let me just go back. I'm just going to go back to this picture to get rid of all the other clutter. Look at this linear strategy. It implies that if carbon concentrations go up a little bit, the response of everybody else is to reduce their emissions. That's a terrible strategic incentive. I'm thinking of how much should I emit? Well, if I emit a bit more, there's all sorts of things that happen. But one of the things that happens is that tomorrow everybody else will be emitting less. That's a very bad strategic incentive. And I think it's this feature which makes the linear equilibrium the worst one of all the symmetric continuous value ones. Whereas here, we have very strong strategic incentives. You stay at this benevolent steady state, or if we go above, then we go way above. So that's what's driving it. Okay, I'm basically out of time. So Let me skip the time trajectories and so on. We have a much more general result. This example was a symmetric game with linear quadratic specification. We've done the same with an isoelastic utility in an early version of working paper of this project. But you can choose any old functional specification given what we give you. You can look at, in principle, at asymmetric equilibria, at asymmetric specifications. Of course, the analysis gets a bit trickier, but I think we provide tools for you to at least start doing that. I had here the more general necessary and sufficient condition. Let me skip all of that. It's similar to what you saw, and I'm not going to say anything about the proof either. So perhaps I'm just going to stop there and rather have a discussion than me keeping on.